Hello, everyone. Welcome to the Developing FPGA PCIe Drivers webinar. My name is Daniel. I'm the Technical Customer Success Manager of WinDriver. We also have with us Daniel Danino. He's an FPGA engineer. In this webinar, we will talk about what FPGA is, what it requires in order to form a PCIe configuration with DMA using an FPGA. And having Daniel Danino, our FPGA engineer, is of a great help also for supporting and advising you, the potential user of WinDriver, on how to successfully run, build your design and run your driver. If you have any questions, you can write them on chat, and I will answer them by the end of this session. So today we are going to talk about from big to small, from the physical to the driver or to the code layer. We're going to talk about FPGAs in general, talk about PCIe's related IPs. We will discuss what IP is. Specifically, we'll show an XDMA design and why it is important to be highly familiar with its configurations prior to developing your driver. Of course, we will talk about WinDriver. We will see the DMA samples we provide that are compatible with several IPs by different manufacturers. And I will mention kernel plugin and show you how significant it can be to improve your driver performance. So let's start in very general. And most of you probably know this. What is an FPGA? FPGA is a board that has a lot of physical features. And you, as the developer or the engineer, can choose which features you want and set the logic. So it's modular. The fact that it's modular allows you to prototype better because you're physically and actually testing the hardware component. You can use it for research or distribution in order to test which design and which features you need in your device, and then distribute it as is, or manufacture a separate device based on the logic you proved working with the FPGA. This is, I know, very general because this is not our scope. We will talk much more about the code and the driver layer. So let's talk about the physical layer first. What is an FPGA and how it makes the magic works? So unlike other devices or PCB cards, on FPGA you have a very dense electronic components or blocks that allows you to implement logic of your choice. So as I said, it is modular, and it's thanks to the physical components the FPGA is assembled from. You have blocks, and we will talk about blocks, I/O blocks for reading and writing, logic blocks, which can be, as I said, modified as per your need. Switch blocks, interconnect. I won't get into the physical matter. I can recommend on Altera's Learning Center. They have great Intel Altera content. They have great videos and the sessions there if you're highly interested in the physical domain of FPGA. So when talking about FPGA, we have three types in general. We have the low end, which which has fewer logic elements. They require minimal memory resources. They have a very low power consumptions, and they're using for GPIOs, bridging, simple logic. The mid-range FPGAs has more logic elements between 50K and 200K. They have moderate memory resources, and they're used for motor control, signal processing, imaging, and so on. And the high-end FPGAs have more than 200K logic elements. They use extensive memory resources. Their power consumption is medium to high, and they're using for 5G technology, AI or machine learning, data center acceleration, etc. So before even talking about drivers, one must know there are different types and tiers of FPGA. And maybe the first thing you need to ask yourself is what is the scope and what will suit you best. Now, there are two types of IPs. So as I said, the FPGA is modular, meaning you can implement or add different logic to it. So the logic splits to two. You have hard IPs, which are physically pre-silicon embedded. Okay, these are not to be modified when designing your design. It has a high performance, okay, since it is physically embedded in the silicon. It has limited flexibility um, for the obvious reasons. The setup is minimal because you don't have too much room for changing the configurations, and do not consume FPGA fabric. Okay, so memory resources, it is not consuming the FPGA fabric. Soft IPs, on the other hand, are logic. Okay, it's a logic. It is mapped into the FPGA fabric. You can add it and you can remove it. The performance is lower than the hard IP, but it is highly flexible, and we will see how you can affect and change the parameters and configurations in a design. It requires optimizations and synthesis, of course, because it's not physically embedded in the device yet, or at all, and it consumes logic elements, of course, because the device needs resources in order to manage and run the design you set up. Another component I want to talk about is transceivers. So transceivers are built-in hardware blocks that send and receive high-speed serial data, converting it to and from parallel data used inside the chip. So there are very, very different kinds of transceivers, but I show you this specific slide, and it is taken from Altera instructions on Agile X5 FPGA to talk about PCIe hard IP. We're going to focus on PCIe hard IP. And this is just an example of what PGA essentially is. It allows you to add different blocks of memory to your device, to your design. And here we have a hard IP of PCIe. So it is 3.4, 3.0, 4.0. You can see the speed, you can see the features, and we know that it is embedded on the device already. You just need to add it in order to activate it and use it, and it will use the FPGA, the PCIe lane, the default PCIe lane that connects it to the machine, to the computer. So this is another thing to be mindful of. Which type of IP are we talking about? PCIe are usually hard IPs, and of course, what it allows, okay? What configurations you can add, at which speed, and we will dive into more details later. We have a poll. It will take 2 minutes. I will start it now. 5 quick questions, and afterward we will continue. Just a second, we're having Zoom issues here. Apologies. Okay, let's continue. Sorry, hi, I'm getting errors from Zoom, and I'm not going to troubleshoot it now. Oh, just a second. It is running. You can see the pool now on the screen. Please take 2 minutes and answer the questions, and we will continue. Okay, 30 seconds, and we will continue. Ten seconds. Okay. Thanks for everyone who answered the questions. Let's move on. So we talked about the physical layer very briefly, I know. Now, once you have your device, you need to start to implement the logic you want on your device. So we talked about logic blocks, okay, soft IPs, which can use for memory bars, DMA. I will talk about generally, mostly on PCIe, okay, from now on. Memory bars, DMA, interrupts, offsets, clocks, AXI connectors for data. This is how it looks like. This is a screenshot from Xilinx design platform. You can see we have the QDMA block, which we have a sample for. I will get to it. Connected support, connected to other building block. And all these links, they include the AXI connectors, they include the configuration control, they include the clocks. So you have a lot of parameters you need to configure in order to make the sample and the device and the design work. This is an example from Lattice Radiant. We see here that there is an IP catalog, okay, where you can choose each the design you want, the IP you want. In this case, it is I2C controller. You have I3C controller. You have the documentation for each one of them, and you should be highly familiar with each logic and which block and how you should utilize it. And here on this in the right side of the window, we can see the physical device, and if you would add the logic to it, you can see how it changes. Okay, so you can actually see physically how things are implemented and embedded on your device. This is again from Lattice Radiant, showcasing IP catalog. Once you choose the logic block, in this case I2C, you can or should configure the components. As I said, sorry, I was thrown out for some reason. Sorry. So we saw the IP catalog, and on each logic block, you can and should set the parameters that will set your design and how it will behave. This is an example I got from our FPGA engineer. We can see here the XDMA design. Again, we will host a webinar talking more thoroughly about this design and how you should implement it. But in general, okay, this is how it looks like. You have the XDMA component, you have AXI connectors for data, okay, and each one of them connects to other logic blocks. You have a counter binary which connects to a clock. I won't get too specific here. Again, due to a shortage of time, but it is important. If you are using a XDMA sample or any one of the samples we are supporting, which I will talk later, you can talk to us and we will guide you through the design we recommend to implement. So after setting up the design and choosing the PCIe block, you have the option to set other parameters like the functional mode, the device port, location, of course, AXI data width, which type of DMA interface option, which type of DMA interface, data protection. You can set the bars for size, values, numbers of user interrupts, whether these are legacy interrupts or MSI interrupts or both, and choose the DMA channel for host to card and card to host, and other parameters. Again, there is a lot to discuss here. We will get more into the driver technicality later, but this is important. And if you have questions on how to set up a design, an XDMA design, to use to correspond and be aligned with our driver samples, you can reach us out. After setting up the design, you will get the information. In this case, the master high address for your XDMA, okay, the one we've mapped. So you are getting this as an output for your design. And again, this is very important to be familiar with all these small details, because you would need to write to those addresses and be very accurate with the parameters you are entering. And now we will see exactly how it is being done shortly. So now we got to the main part. We talked about the physical layer, the logic or design layer, and now we will talk about the driver. Okay, so you completed the design part, everything is working, right? But now you need to plug it in to the PC or to run it via your operating system with very specific tasks and features. So how can you make it work? So in general, I want to talk about WinDriver. If you're not familiar with it, WinDriver is a driver development toolkit. We have a very friendly GUI interface, allowing you to add parameters and define memory ranges and access registers, and enable listening to interrupts and read configuration space data, just like that, without the need to code anything. This is a GUI interface, as I said. You can download it for free for 30 days on our website. And this is how it looks like. You set the parameters in a GUI application for any PCIe device. I'm not talking just about FPGAs now. You generate your code. This is the code you're generating. We will see how a code looks like shortly. Building it, and you get a user application, okay, which allows you to do many things like reading and writing from the device, start listening to interrupts, perform DMA, using kernel plugins, and so on. So we know that manufacturers, AMD, Lattice, Altera, Intel, provide a default driver for your for the XDMA design or QDMA design or BMD design. So why using WinDriver? So the first one is the availability. The first advantage, we are working with every PCIe device or configuration. So if you worked, for example, if you're working, for example, or testing several FPGAs, you can use WinDriver and use the same code and same functions name and so on. We have a high customizability. The default drivers usually are not flexible at all. If you can edit the code, you can do it on a very limited basis. And then with WinDriver, you don't have that issue. It is fully customizable. You can add your own functions. You can use our APIs, of course. So this is maybe the biggest advantage we have over the default drivers provided by the manufacturers, the conveniency. So WinDriver, again, has a GUI, it is a GUI application, and we have a debugger, our own debugger. We have our kernel module loader and unloader, and you are developing everything in the user mode. Another thing which is great is the cross-platform compatibility. So we support both Windows, Linux, Mac, and we encourage you to download WinDriver and test it across all platforms, and not only to install it on cross-platforms, but also to build your driver on different platforms. So if you want to distribute your FPGA driver to Windows or Linux or Mac, you can do so with WinDriver. And of course, as I mentioned, we have an FPGA engineer in-house with the specialized FPGA support. So if you encounter issues, questions regarding how to implement your design to work with our samples, you can reach us out, and we have an expert in-house to assist. I'll show you the samples right after that. They're coming with performance test, customized DMA IP data with offset descriptors, interrupt handler, built-in interrupt handler, okay? DMA mechanism, kernel plugin to be incorporated in the DMA and other functions. The samples we provide are based on Xilinx or AMD QDMA, XDMA, and BMD designs. We support Altera or Intel Avalon MSG DMA samples, and we've just recently added Lattice. Again, my apologies. I got thrown off again. Let me share the screen. Okay, let's go. So what do we offer? This is just an example of how WinDriver does. This is just an example of what WinDriver does and what is our main benefit. We have functions, okay? We provide high-level API, meaning user mode API, which performs operations on the kernel mode. We have the scatter gather buffer lock function. This is how it looks like. Everything is documented both in the code and on our website, which basically locks buffers to perform DMA scatter gather. Also, the same one for contiguous. We have a function for unlocking the buffers. We have an interrupt handler function, which does a lot of cool things. We have a webinar dedicated just for this function and for interrupt handlers. And now we will see the flow, okay? How are we doing, how are we allowing or supporting the DMA operation based on your design? So in this case, it is based on Lattice Certus Pro and example. The source is the host in this case, and the target is the DMA or the FPGA. And we want to move data from the host to the buffer, to the FPGA. This is how it looks like in the code. I will open the code and we will go through it. But essentially, in the CPNX Certus Pro DMA, we have a struct showing the scatter buffer, the data, okay? Data buffers for the data transfers. And we have the descriptors containing the information on the data buffers locations. It is changing between devices. Okay, not every device will have the same buffers or the same elements. In Avant, for example, we have a status element, but this is why you need to be highly familiar with how your device works. But for us in WinDriver, it is the same functionality. We need to create, right? So we need to create the buffers, move the data, and then send it to the target. So the first thing we need to do is to create the data and descriptor buffers using the SG bufflock function. Okay, this is how it looks like, WDC DMA SG bufflock that locks the buffer for the data and the descriptor. Then we need to configure the descriptors, okay, taking the information from the source and then moving it to the buffer, configuring it. Then we need to configure the device with the descriptor's address. Okay, writing the descriptor address to the device so it will know where to access the data buffers. Okay, and once the DMA is initiated, again, it is being initiated from the FPGA. We start moving until we get all the data moved to the DMA or FPGA device. So in this case, in the Certus Pro NX, the data, as you can see here, when the last descriptor is transferred, an interrupt is raised. Okay, you can see here CPNX descriptor control int, and if the interrupt is raised, that means that we can clean up the routine and unlock all the buffers and delete all the data from where we've written it to. So let's dive in the code and we will see how it looks like. So here we have WinDriver 16.4.0 folder. If you download WinDriver and install it, this is how it looks like. We have a sample folder. We support different languages, Java, C#, .NET, Python, Visual Basic. And if I'm entering C, okay, C language, we can see that we have here Altera, Lattice, Xilinx, and other samples, PCI diag, which you have a webinar on, USB diag, and so on. Let's start with the Xilinx XDMA sample. Okay, I like to work with Visual Studio and to open my code using CMake file. We're going step by step here. Okay. So I'm opening the CMake file. I will give it 1 or 2 seconds to load everything. Okay, here we have it. And let's see what it includes. So here we have the xdma lib.c. Now you can do the same thing, generating a code from the wizard, right? And it looks the same. The code looks the same. Here we have all the major functions needed. This is the logic in order to open the driver, to close it. All of these functions are already configured. Reading addresses, opening the device, closing the device, raising interrupts, and so on. Now, the crucial part is when we're talking about FPGAs and customizability, is set here, okay, in the xdma lib.h. This header file contains different parameters that are unique for the design, okay? We can see here that we have power management event handler functions type. We have the host to card, card to host, control register bits. Okay, these are device specific. And again, already defined in the driver. In the code, we have the offsets, which we all know are very critical to perform operations. And all these are based on the datasheet of the manufacturer. In this case, Xilinx, okay, for the xdma. So everything is predefined here, and you can also add registers. Now, if you want to set your design differently for your own purpose, you need to make sure to change the offsets that are set here to ensure the compatibility between the driver and the device. So again, I won't get specifically to each offset configuration, but know that this information is stored here. We have the lib.c and we have the lib.h. Now, if you haven't used WinDriver prior to that, you saw I just need to build it and run. I will get an error because I don't have a Xilinx device connected to my PC currently. But all you need to do is build it. It is compiling without errors. And if you have, in this case, a Xilinx device connected to your PC, it should work and you can access the application. Now, I do want you to see how the application looks like and how it works. So we've recorded a video. In this case, it's the Lattice Avant. And we'll take it slow because this video is moving fast. When you open the application, in this case, it's in Linux, you can see that when you open the device, you get the device details, memory bars, interrupt options, the generation of your PCI, and whether you're using a kernel plugin or not. If you are not sure what a kernel plugin is, we will get to it by the end of the session. So you have a menu, and this is the default menu. You can scan PCI bus, find and open PCI devices, read or write memory and I/O addresses on the device. Again, you don't need to code anything. You have this built-in options on the PCI diag sample or utility or on other samples. But if you are using the sample, you need a supporting device. You can read or write the PCI configuration space, perform DMAs, and register or unregister plug and play and power management events. In this case, our developer choose to perform DMA. Okay, this is the sample, sample we want to demonstrate, or the feature. So once they clicked 5 to perform DMA, we've got a new menu. Perform a DMA transfer, perform a DMA transfer to device, from device, and compare the buffers. Or 3, perform DMA transfer to device with incremented data, perform DMA transfer from device and compare the DMA buffers, or measure the performance, which is a new feature. Sorry. Okay, we've seen that. Our developer chose to perform DMA transfer to device, from device, and to compare the buffers. And now the application asks, what is the data pattern? Our developer enters that beef. We need to enter the number of packets to transfer. Okay, 100. And we are being asked to enter the device memory address for transfer. Okay, which again is critical. So you need to know your device well. So we've entered the relevant address, memory address, and then we can see, first of all, that the DMA is using kernel plugin. We have an interrupt received. Remember when we said that when a DMA ends, an interrupt is raised. So an interrupt was raised or has been raised. We can see the 100 dead beefs that were sent with the DMA. We get a message that the DMA transfer completed successfully, and that we ask the application to compare, right, the DMA buffers. So the write buffer and read buffer are identical. Okay, the DMA interrupts disabled. So we not only have a DMA implemented here, we also have an interrupt handler implemented here, which helps us to initiate and perform the DMA. Okay, this is the first demo. The second demo is for DMA performance test. Got thrown off again. I'm sorry. See if we have it on a higher quality. Yes. Okay. So let's go to the start. Again, we can see, right? You can see my screen. Yes. We can see all the details. Here we are talking about CPNX DMA diag. We choose to perform DMA, but now we don't want to perform DMA, we want to measure the DMA performance. Okay? The menu asks us, do you want host to device performance, device to host performance, or both running simultaneously? In this case, we will test the host to device performance. We enter the details of the DMA we want to perform, and we got it. The DMA test ran 1,000 times using a kernel plugin. And here we can see how many bytes were transferred, in what time, and the rate. Okay, now we are doing the DMA device to host performance, setting the DMA parameters, and again, getting the performance data. And in the last part, we are asking to perform both host to device and device to host performance test, setting the parameters and getting the information of the DMA just after it ends. So this is how it looks like. I said I would talk about kernel plugin. Okay, let's go. What is a kernel plugin? We said that WinDriver allows you to develop code or drivers from the user mode and to affect the kernel mode. We have an API that has user mode and kernel mode functions that are corresponding, and it allows you basically to have your code written on the user mode, debugging it in the user mode, but it will act and operate in the kernel mode. Now, there is what is called a context switch, okay? Switching the context between the user mode and the kernel mode, which can be time and resource consuming. If we're talking about time-sensitive applications and performance-critical applications like DMA, you want to eliminate factors like context switch. WinDriver developed a thing called kernel plugin, which allows you to take your user mode code, you almost do not need to change it, and running it in the kernel mode. Now, when talking about interrupts, it is critical. We saw that when a DMA ends, an interrupt is raised. Now, it can get to 10,000 interrupts per second in some applications. And here we can see that when we ran the Certus Pro NX samples, which is PCIe 3, we got hundreds of percents of increase with kernel plugin from host to FPGA and from FPGA to host. Okay, we see huge numbers of performance increase just by eliminating the context switch. In Avant, we see the same. With kernel plugin host to FPGA, we have more than 60% of increase in performance. We have around 80 when talking about FPGA to host. The reason that these numbers are lower is that the Avant is much faster. And we know that it is much harder to optimize and improve faster things, let's say. So, but you can see also around 70-80% of increase in performance is big. So if you look for ways to improve your FPGA PCIe driver performance, kernel plugin is a way to go. I'm leaving time for questions and answers, so feel free to ask now on the chat. You will get the recording. I hope it will be saved in one take after the webinar. We are planning to share it. The FPGA board for a reference. So we talked about the Certus Pro, the Avant. I showed you the XDMA sample code, and I will go back to the devices we support because it is important. Okay, these are the supported devices. Okay, just a second. Sorry about the technical issues. This is really out of my hand. So someone's asked here, I want to send, sorry. I want to send the camera data to PC using I2C commands and go through PCIe sensor-generated data. Does your solution useful for this case? So our samples were built based on specific design, and I can't say that enough. What we do support different designs, and we do support other configurations. However, you need to be highly familiarized with the parameters and details of the design and the blocks. We can help you with that. Don't hesitate. Contact us, ask for help. We can have a technical session. So I won't say no. I would say yes, but it would need more details and further investigation from both ends, us and the user. So someone asked, in the first demo, the interrupt is actually raised from the device side or from the OS side? That's a good question. So the way it goes, the interrupt is a physical component in the device, right? The driver from the operating system and listens to interrupt. If you find this interesting, go to our YouTube channel or our media section, and you can find an entire webinar about interrupt handler and how it works. So the operating system, let's say in this case, listens to interrupt, and it is being raised by the device. This is the answer. Another question: how the data is validated on the other side of the performance test? This is a very specific question. You can send us an email and we will try to answer it. Does the kernel plugin activates on the interrupt from both sides? So the kernel plugin sits again in the kernel mode. It listens to interrupt and receives them and trigger them from the kernel. It raises the interrupt on the device. There are general questions about PCI that I'm not feeling qualified to answer here, but you can send me these questions and I will try to help. So again, someone's asked here, different controllers cores may have slight different initialization sequence. How does it handle? So our code, our samples can work with any device. Okay, we haven't encountered a device we do not support. The question is, what are the configurations of your specific device? And if you set the parameters right on the driver that are aligned with your manufacturer specs, it should work. This is how it goes. So this is a great question. Someone asked here, from someone who uses Quartus for the design step, how can we use WinDriver to get a more efficient driver? Once you've done setting up your design, and I know this is not like a one step, you always go back to the design. But once you have a working design, um, download WinDriver and open it. WinDriver will identify your PCIe logic block or FPGA as a PCIe, and it will handle it as every PCIe it ever encountered. So this is the answer. Once the design is set up, and go to the machine that is connected to the FPGA, download WinDriver, open it, and you can choose your device from the list. Someone asks, when the data is required to send from the operating system to the device, how the device comes to know that the data is available in the driver buffer. More specific questions about how the sample work, because we need to go deep in the code and how it works. You can send us an email and I will address it later. We have still a few minutes, so I want to show you WinDriver and what we're talking about here. Just a second. Okay, so this is how it looks like. We have a bigger window. I will show you it shortly. Choosing a new project. And we have a device list. These are all the devices that are connected to my PC right now. This one I have the license for. Let's call it FPGA demo. Sorry. I won't get into INFs right now, but this is WinDriver. Okay, this is the tool. Once my device identified the PCIe, I was able to open it, and I can see the configuration space data. I can see the bar, the memory bar, which I have only one here. I can add access registers, read or write to the memory, listen to interrupts, add transfer commands that will be initiated after the interrupt is raised. I won't get into other features right now. Generate code. Okay, so here I can choose the specific sample I want support for, and the language. I will choose C. I will choose a makefile for Windows. I can add the kernel plugin or generate a DLL. And just like that, I have a project. Okay, this is the project that was generated. Remember it, I will have to close WinDriver in order to run my driver. Now let's open it on Visual Studio. Okay, FPGA demo, CMake list. I will give it a second, set up. And here I have my code, right? Everything that I've set on the wizard is now available here. I have the lib.h folder that contains device-specific configurations, which are missing now because this is not an FPGA device that I've opened. Now all I need to do is to build and to run. Okay, and this is how it looks like. I have the FPGA demo diagnostic utility. It is failed. Okay, because this is just a setup thing, but this is how it looks like, the flow. Okay, you open WinDriver, you set up the parameters, choosing your device, set up the parameters, generate the code, and you have a folder containing all the code you need in order both to build and to distribute. So this is WinDriver, and I really recommend you to try it. If you don't have more questions, then thanks for attending, and feel free to contact us regarding any other issue.